So there are a few ways that we can determine delta H of a reaction. One is through calorimetry, where we would experimentally measure the heat given off of the chemical reaction. And that's fine, but we might not always have access to the expensive equipment or materials or the time to do these measurements in the lab. So there are three different approximations that can be used to approximate the delta H of a chemical reaction. They are Hess's law, heats of formation, and bond dissociation energies. So in the next several videos, we're going to look at each of those as ways of calculating delta H for a chemical reaction. In this particular video, we are going to look at Hess's law and using that to calculate delta H. So Hess's law says that the delta H for an overall process will be the sum of the individual steps. Let's say that we have a reaction where A produces B, and this has a delta H value associated with it. And then maybe B produces C, and this has a separate delta H value associated with it. Well, we can use Hess's law to add these together and say, well, A plus B making C, and this would have a delta H value, let's call it delta H3. So what we have is if we start here with A, maybe we need to put energy in for this process to happen to get to B. And then B needs more energy to get to C. Well, to go from A to C directly, this is delta H1, delta H2, we would need to put in this amount of energy, which would be delta H3, according to my equations over here. So we can say that delta H3 is equal to the sum of the individual steps, delta H1 plus delta H2. So what this means for us is that if we have two chemical reactions, we can combine them in such a way that they add together to give a whole reaction. Let's look at our hydrogen combustion reaction in the context of Hess's law. Let's say we start up here, we have my hydrogen and oxygen reactants, and then I'm going to release some amount of energy to produce water, vapor, and then I would release some smaller amount of energy to produce liquid water. So we have step 1, step 2, let's call it delta HA, delta HB, and overall this entire process might be labeled delta HC. So delta HC, according to Hess's law, would be equal to the sum of the individual steps, delta HA plus delta HB. And that it's as simple as that. So let's look at an example together. So here's some information that we can use to apply Hess's law. We have two equations, aluminum reacting with oxygen to produce aluminum oxide, iron reacting with oxide to produce iron oxide, but what we don't know is the heat of reaction for when we combine aluminum with iron oxide to produce the aluminum oxide and iron. So we can actually add A and B together and do a little bit of math with it to get an approximation for the heat of reaction of this third reaction that we're interested in. So I'm going to look at this and say, okay, I need aluminum as a reactant. So I'm going to find aluminum in my equations up here. So equation A has aluminum. So I'm going to say 4 aluminum plus 3 O2 gives 2 Al2O3 solids. All right? And this says 4 aluminum, but I only need 2 aluminum. So I can account for this fact by multiplying this by 1/2. Okay? So that gives me 2 aluminums and 3/2 oxygen and 1 aluminum oxide. Now, anytime I do something like that to the chemical equation, I must also do the same to my delta H value, so I'm going to multiply this by 1/2, and this will give me negative 1675 kilojoules. Right? So we're paying attention to the numbers in pink now. Then the second piece I need is iron oxide. And where is iron oxide here? Well, it's listed as a product in equation B, but I need it as a reactant. So I'm going to flip equation B around. So I'll have 2 iron oxide plus, whoops, no plus here, producing 4 iron and 3 O2 gas. Okay, and this has a delta H associated with it. Before it was negative, remember I flipped it around, so that one property of enthalpy we have to remember that the reverse reaction will be equal in magnitude but opposite in sign, so it'll be plus 1648.4 kilojoules. And now we have to think about making any adjustments. Well, I have 1 mole of iron oxide and here I have 2, so I need to multiply it by 1/2 again. So this would leave me with 1, 2, and 3/2 oxygen. We'll multiply this by 1/2 as well, and we'll get positive 824.2 kilojoules. Okay, are we there yet? Well, the final thing that I would do is check, okay, I have aluminum and I have iron, and aluminum and iron as products as well. So then I think I'm okay. Let's add this all up. So I have, taking from the reactants starting at the top, 2 aluminums plus 3/2 O2, then going to the reactants below here, plus 1 iron oxide. The phases are not super important. I tend to forget to write them, so if you do see me miss one, that's not super critical. Products are going to be aluminum oxide plus 2 iron plus 3/2 O2 gas, and then delta H for this would be simply adding these up. So negative 1675 plus 824 gives me negative 851.5. So I've done some rounding here. Gives me a little bit of variation in the decimal. And then we can cancel out anything that appears on both the reactant and product sides. So aluminum is good. The oxygen appears twice, so we can just cancel this out. And so that won't appear in my chemical reaction. I have the iron oxide, the aluminum oxide, and the iron. And then we want to just check back to the equation of interest, right? So does this match with this? So I have 2 aluminums plus the iron oxide, giving aluminum oxide plus 2 irons. So we have a match, and this would be the delta H of the reaction according to Hess's law. So I want to give you a chance to try this type of problem solving. Again, to recap, we take the 2 equations that we know, and sometimes we can look these up in the literature, and then the equation that we want to know, we have to pull the information we need from the 2 known equations, rearrange it, and account for the appropriate stoichiometry, and add them together ultimately to give our final answer. Okay? Thanks for watching.